VLSos here. This is a video lesson on the definite integral. Let's take a look at what is hopefully a very common project in calculus or pre-calculus, and that is estimating the area under a curve on an interval. We could use the symbol capital A for area and ask the question with this notation under a function f, and give the interval in the parentheses as well from A to B. And what we mean by that is if we have any kind of function and an interval in the domain, we mean to find an approximation for the area between that function and the x-axis. We have several methods of estimating that area. One of the most typical ways to estimate it is to use rectangles, such that a rectangle approximates the area, and if we add up a number of rectangles, then we can get an approximation for the entire area. The more rectangles we use, the more accurate our estimate, but it's still an estimate. So we use the approximately equal to sign and sigma notation to organize summing up rectangle areas. We need an index for sigma, so we start typically at 0 and go up to n-1, where n is the number of rectangles that we're going to use. The argument is for the area of one of those rectangles, f composed with a plus delta x k gets the height of the rectangle, and delta x is the base. Now, we know in practicing this method that the more rectangles we use, the less error there is between the estimate and the exact. So if we conceptually are able to use an infinite number of rectangles, then we will approach getting an exact area under the curve. We can then get an exact area exactly equal to, as a concept, taking the limit as the number of rectangles n approaches infinity, where n is used as in the upper index of sigma, and we still have the argument f composed with delta xk times delta x. This right here is an impossible calculation to do by hand, because we would be using the argument of sigma an infinite number of times. There is software where we can compose sigma notation this way, which includes the limit, and the software can handle it and get the exact area calculated. But we have a method for calculating the exact area, and that is to think of this concept, this notation that stands for or represents the concept of a limit, an infinite limit, and the sum, or sigma, and we wrap that up into the symbol, which is an elongated s. And we call this symbol an integral sign. It's a stretched out s. S still stands for sum, just as this capital Greek letter sigma is S in the Greek alphabet, and it stands for sum as well. So we changed the sigma s to this integral s. The function, when we change the sigma notation into the integral notation, does not need any longer the argument a plus delta xk. We can now work with just the function itself, f of x, unmodified. And this delta x, which represented the change in x, then changes form to be a dx. So the argument of this new representation still has the components. The sigma has become an elongated s, the function is now just the function unmodified, and the delta x became a dx. This integral symbol encapsulates the concept of summing an infinite number of things. Encapsulates the concept, but we no longer have to write the expansion of sigma and actually do the calculation by hand. We can work with this as an integral with using calculus techniques. The bounds, which we're trying to find the area under f, are still a part of this, we put those bounds here, the lower bound and the upper bound, on the different ends of the integral sign. This piece of this integral notation, the function that's inside the integral and the dx, is called the integrand. This dx that came from the delta x is often what we say is with respects to. Which will make more sense when we practice this notation and use it in the future. This is the integral symbol. And the a to b are the bounds of integration. For example, if I was asked now, what is the area under a function like g from 2 to 5, and we'll provide the g function and its graph here. Let's imagine that the g function is x minus 3 all squared plus 1, which is a transformed quadratic. The area under g from 2 to 5 would be the region shaded between the x-axis. And if I wanted to find the exact area under the curve, then I can use the integral, not sigma. Using the integral, I put the bounds from 2 to 5. The integrand is the function itself. And then the dx means with respects to x, which we need to talk about and make sense of. We're not ready for that. We'll do that in the future. And this integral is equal to the exact area that we're trying to calculate. This is how to set up the integral. Now, using, or the process of finding a value for this integral is a process of integration, and there are several techniques. We'll have lessons on how to do that in the future. This integral is called a definite integral because it has bounds. If an integral represented the entire function and there was no beginning, an end, or no lower and upper bound, we would call it an indefinite integral.